Hi, welcome back to my channel. This is a talk on what I call the mild defense of object-oriented programming. This was kind of inspired by the talk given by Casey Muratori on what he called "Oops," the 35-year-old the 35-year-old mistake. And what that video was about really goes into an excellent amount of detail about programming languages and the history of object-oriented programming languages and how they influence the design of C++. And he talks about certain ideas that he felt were maybe unfairly dismissed that could have been better suited than some of the concepts that were introduced in C++ in terms of class-based inheritance and so on and so forth. Again, if you haven't, please do watch that video. It is long, but it's very well done. And if you are interested in programming at all, it's an excellent historical background, and it's quite engaging to watch, and it's very well done. What my presentation hopes to do is I'm just going to try to cover some areas that that presentation didn't do. I just want to bring up that that's not a fault of the original presentation, and that you always have to choose what material you want to cover. There's always more that you could cover, and there's just not enough time to do it. And certainly my presentation is not going to be any more exhaustive than any other presentation on the subject would be. The first concept I want to kind of bring up that Casey talk didn't really kind of go into a lot of detail about, but is important in terms of the history of object-oriented programming, is the notion of software reuse. And I have a lot of experience in this area thanks to the work I did with Martin Griss, who is also called the Reuse Rabbi. He worked at HP Labs and did a lot of great papers and research on how to make software more reusable inside an organization as well as between multiple organizations. Software reuse has its long and interesting history. Someone had to come up with this notion of composable blocks and reusable software. And really what it came down to is there's a paper in the 60s that came around the same time that Algol was being developed called Mass-Produced Software Components, in which the idea of components being put together to create software much more in the vein of how a industrial product was put together by quickly assembling certain components kind of brings up that idea, this concept, what would we have to do to get there? And what's interesting is that a lot of some of the work that was being done also on what was called CSP, communicating SQL essential processes, and message passing really influenced that work because people quickly noticed that these communicating SQL processes could be a foundation for creating those reusable components. Of course, the C++ programming language reference itself talks about the reuse of concrete types and why class-based inheritance really helps with reuse. The notions of encapsulation data hiding and later things like list substitutability were designed at first to enable reuse of software and had a secondary consideration in terms of making it software better. But the thing about it is that these concepts, while people try to make them as simple as possible by supporting them in languages directly, it was accepted that this was actually more difficult to do, but that the ability to reuse this code to evolve it carefully was worth the overall effort. That being said, in software reuse, there is a notion of the rule of threes, whereas if you can't think of three different ways that this is going to be reused in the future, sometimes the additional effort that is needed to make software reusable or more reusable isn't worth it. And so I think a lot of people actually, when they talk about things like solid, don't acknowledge that there is a cost to this up front, and you have to be careful about making sure it pays off in the end. All in all, though, the inheritance-based approach and class-based approach in object-oriented programming has led to many successful reusable libraries. And if you take a look at C versus the C standard library versus the C++ standard library, you can see the growth there. And if you look at what's available now in modern programming languages, we take for granted the idea that we have things like packages that you can do, where you can quickly import third-party blocks of code into your environment and start to use them. And if you didn't have concepts like classes that you could subclass, the kind of notions that came from Smalltalk in terms of dynamic instance, But all of this wouldn't be possible without the kind of increase in productivity that these OOP provided to regular programmers in terms of being able to do things like develop more complex software. And all of this was kind of, again, driven by this notion of reuse. And there's two major factors that brought into this. One was that these C++ desktop libraries for doing desktop GUIs were very useful. And also a major player in this was the notion of the component object model and ActiveX from Microsoft, which kind of used some ideas from classes in terms of what we would now call an interface. And the notion of an interface, which was basically a way of basically reusing compiled components at runtime and to be able to interact with them as if they were classes. That was incredibly successful. And if you take a look at Visual Basic and how it allowed people to visually design GUIs and reuse these components, it all created this explosion in desktop-based software in businesses, whereas before it was just too complicated to do any of these types of stuff. And this led to a massive amount of demand for more and more software and really, really jump-started the use of computing in a lot of domains. And really, when the web came along and further accelerated this notion of being able to want to access these kind of applications, but be able to do it in a much more fluid and fast way, the idea behind class-based object-oriented programming was the impetus for a lot of this happening. So it was massively successful. And some of these libraries are used today. A lot of people still develop software using things like GDK or Qt, or Microsoft C++ is still used in a lot of cases. And one of the things I find funny is that people talk a lot about how, the web will replace all this kind of stuff, but fail to note that basically Chrome itself and Chromium is a very, very well thought out C++ library and program that uses things like classes and subclassing and inheritance very carefully to create a very good cross-platform desktop program. And no one is calling for the Chrome base to be replaced by any sort of TypeScript or any other type of thing else, because A, it was very well designed, and B, of course, there's a lot of inertia there. But at the end of the day, it's hard to argue against some of the successes that C++ and later on languages have had in creating programs that had a fairly long life and have been maintainable and evolved over a very long time. So, if the object-oriented approach was a mistake, and I know that Casey's talk was really, and the title was very much a tongue-in-cheek type of thing, and his criticisms of C++ in the current environment are much more nuanced. But if it was a mistake, it was an incredibly successful one. And what's interesting is that I think the current attempts to kind of, what I would say, ignore or replace that paradigm that are ongoing, don't get me wrong, I'll talk about them, but have also led to equally complex ecosystems that often exceed their predecessors in terms of difficulty in developing new systems. And what I say that is that while the web has made it easier to provide software to people, it has not created a quantum leap forward in developer productivity. And the reason I say that is if you look for the demand for programmers in general and how it greatly expanded, the reason for that is that we have not seen a big leap in productivity for a single programmer compared to what happened when we had these C++ libraries and developing these first desktop programs. And that jump may never happen, so that may never happen again. But at the same time, it's one of those things where it's hard to say that the current web types of frameworks have really pushed things forward. And I think there's good arguments to say that they've actually stalled in a lot of respects, and also have led to worse software than we were used to 10 or 15 years ago, when more of the desktop GUI application was the more common type of thing or program that most people expected and used. So I want to talk a little bit also about when Casey talked about records or constraint systems. If you haven't seen the source video, this will make less sense to you, but basically Casey talks a lot about Sketchpad and rightfully so, because Sketchpad really sparked a lot of research into object-oriented programming and reused some of the ideas that were going around at the time. And not only that, but was really influential as being kind of the first GUI program itself, really being the first thing that people could point to and say, here's where someone uses a specialized input device beyond a keyboard to interact with a graphical display. And it's kind of funny now to think about that, but that was a new idea in computing. People had to use punch cards and teletypes before that. So it's an incredibly influential bit of work. The work that either Sutherland then went on at the University of Utah, basically invented the foundation for modern computer graphics and also computer-aided design. And as a side, because of modern computer graphics, basically the entire notion of video games can be directly tied back to all that work as well. So very influential, very good work, very interesting. And so it's great that Casey brought that up and kind of goes into depth of some of the ideas that he brought up in that his PhD thesis, which was that was developing Sketchpad was part of his PhD. So I will say this in case he talks about this. If you talk about a programming system in which data is transparent and is organized into records or fat structs or the like, and then is being mutated by outside constraints and functions, is very powerful. But I'm going to focus mainly on constraints here. The problem is that system that Sketchpad kind of explored in terms of constraints. And let me put this in a little bit of context. What Sketchpad had was not just the notion that you could draw arbitrary lines on a display, a vector display at the time, but you could say that things are like, these set of lines must be connected so that they form a polygon, or that they need to be parallel or perpendicular and things like that. And so made it very useful for coming up with geometry that wasn't just like some random lines. So that, and Casey talks about how that's a really cool and is a very powerful paradigm, and it was. The problem is that in general it's too powerful. And this may make people scratch their heads, but what I mean by too powerful is that if you look at the terms of basically what we call computational complexity, or how long does it take to run something, there's something called the Boolean satisfiability problem, which is by itself a constraint solving problem, and is the first type of problem that was provably called NP complete. That basically we do not know of any polynomial type of algorithm that will solve it, and that in general there's an exponential amount of growth in solving these problems. And all the Boolean satisfiability problem is that it's very simple. If I have a set of Boolean propositions with variables, given those propositions and all those variables, is there a set of values for each one of those variables that will solve that system? So is that system consistent, which means, it can be true if all these variables line up, or is it inconsistent? It was always false. That in general is very difficult to do. And that means that ultimately itself, constraint-based systems have this exponential explosion unless you do some very careful work on restricting the domain, the number of constraints you can express, and the number of variables that they work on. You have to do this very carefully to keep the entire solution space from exploding. And what I want to point out is that there is a lot of work in programming languages around the notions of constraints and goal solving that has its own history. If you take a look at Prolog, and logic programming is an excellent example. There's also was work on what's done as theorem proving systems and trying to come up with some ways to not have to have these general NP complete problems, but still try to express some more interesting types of things in terms of provable theorems. There's a lot of work done there. And not only that, but in an abstract sense, if you take a look at programming languages themselves and the whole notion of types, type checking itself is a constraint problem. You can really think of it that way. And so if you take a look at things like, for example, the F unification algorithm from ML, which was kind of the most important work done on type inference that you see in other languages, it was well designed such that it was a solvable constraint problem versus being inconsistent or in general take too long to run. But if you take a look at types, if you use types in general and you expand them into certain areas, they can explode in terms of complexity as well. And when I talk about TypeScript in this talk, I'll give you examples of that. So the next thing I'm going to do is I'm going to move on now to reviewing some modern object-oriented programming and language concepts. And I'm going to talk about domain-driven design and design patterns, which he brings up. And he's fairly critical of some of these concepts, and I think some of this criticism is very warranted. So let me just kind of go into a little bit of the background on how I see this. Domain-driven design is really where things can kind of get complicated in terms of how people use it, and there can be a lot of arguments over it. And the main issue for me is that this domain-driven design and design patterns are taken to be prescriptive, not descriptive. And what I mean by prescriptive is that, excuse me, when developers look at it, there's two types of things. It's basically, first of all, let me backtrack here. I don't necessarily say that developers that look at this and say, oh, this is prescriptive versus descriptive, are misunderstanding it or have a skill issue involved with, oh, you just didn't get it. Because this misunderstanding is very common, it's very consistent. And the reason being is the way these ideas are presented in books and by other people really strongly suggest that these concepts must appear in good code. That if they aren't there, then your code is potentially suspect, or worst case, is suspect. Compared to, well, the reality is that they were actually just mechanisms to address issues in essential complexity in software as they arrive when you're dealing with coding in day-to-day practice. And given all that, it is very, very difficult not to say, oh, well, I have to have a certain amount of patterns or a certain amount of domain-driven design in my code to make sure it's good. And if you take a look at some like enterprise frameworks or things that were happening in certain what people we call quote unquote enterprise frameworks, or a classic example is a lot of Java frameworks that came around at the time, like Spring and so on and so forth. It seemed that they had to have a certain amount of patterns and a certain amount of domain-driven design, and like it or not, that's what you're going to use, and didn't really basically kind of swept the complexity that was going on, the verbosity under the table, and that basically all the things would work out. And basically, it got to the point where some of them almost looked at it as like, well, if we don't pile it all on, then we're not going to have something that's truly flexible. And really didn't understand that, no, you just can't willy-nilly just add these things in there that aren't addressing real problems. And it did get to a point of ridiculousness. For example, there were systems, and they don't do this anymore because they did realize it was getting ridiculous, but there's times when you have Java libraries that would have factories for factories. So abstraction on top of abstraction on top of abstraction, it was really getting out of control. And that is absolutely a valid point of criticism. Now, only that, so given all that, and basically that, you can't just apply these things willy-nilly and hope to get better software out of this, even if you have a better understanding of domain-driven design, it's still very hard to understand that basically when we're dealing with software, you're always dealing with at least two domains. And the thing about it is you're dealing with the natural domain, the reason users are using your software and how it maps to the business or other problems that someone's trying to solve. And also, but the domain of computation and software itself in terms of the concepts of it runs on an operating system, uses things like files, databases, I/O, networking, so on and so forth to get its job done. You have to marry those two to get software to work. Those are two separate but intersecting domains. And in even larger systems, there's a third domain that comes in. In fact, to get certain things done at scale, or if you're overly ambitious about what scale needs to be, you need to think about how the software splits across multiple computational units, multiple servers, and interacts over a network to get jobs done. So that's the third domain that comes in a lot of times. So managing these three domains is really, really complicated. If you look at domain-driven design, one could come to the impression that, oh, if I just correctly map the natural domain, that the rest of it will fall into place. And that's not true. The problem is that you do have to have a fairly good grasp on the natural domain, but you still need to marry it with that software domain to get things to work. And if you take a look at the successful kind of libraries, I'll take example like, GUI libraries themselves. A lot of what GUI libraries do is that they really, a lot of their complexity and their hierarchies go into managing the reuse of the computational domain. It has nothing to do with the natural domain. So if I was to take a look at a GUI and say, oh, I have buttons and sliders, there's very few things about how they're externally presented that are parts of the natural domain. And take a look at GUI frameworks, it's very much about, oh, how do you get these things to work together in terms of, I have to draw it on a screen. I have to track these events. I have to make sure that each of these components I'm putting in a GUI are consistent. How do they grow? And that's much more about the software domain itself than the naturalist domain. And of course, for those libraries, that makes a little bit of sense because this was really to kind of enable someone to use these and not have to develop all this stuff and also develop all the stuff in the natural domain to get a useful GUI program. But again, given all this and all these reusable libraries, there still has to be some intersection between what the naturalistic domain is and, again, the domain for software itself. And this is where a lot more work needs to be done and understanding how to address this complexity. And I would say that this is where the art of programming really comes down to it. When someone looks at it and says, what's a good architecture or a good design, it's managing that tension well that really stands out. Of course, the reason that people use design patterns in DDD, and not only that, I will argue for class-based inheritance and data encapsulation, is it does make code much more resilient to decay, but easier to grow and evolve. And that still comes at a cost. And that cost is not insignificant, and it cannot just be like swept under the rug. And again, it is not justified if there's not enough reuse or the cost savings down the road. And in the current environment, what is very difficult is that it is much harder now because of the web and that rapid cycle of being able to put out programs to be able to properly prototype, put out things and really go, well, you know what, this isn't done yet. This isn't baked, but we're learning, and be able to do that process and be able to do it in a way so that you do not have to worry about all these reusable concepts at front, because you know that you're taking what you learn and shoring up the code base when you have a better understanding of your problem and where you want to go. Instead, developers and frameworks increasingly have to backload all this stuff into the very frameworks themselves because there's so much pressure that the first website that you get out there that does anything at all will be put out there because management wants you to push it out there. And everybody wants the software out there as quickly as possible. Even the developers. Developers are excited by getting out their software out there in front of people. And so if they don't do this, they know that there's going to be a significant amount of pain and technical debt that will be built up down the road to get this to scale and evolve and change. And the thing about it is that we know historically that the vast majority of organizations do a very bad job of this. The amount of rework and the demand for rework and editing on developers is massive compared to what it used to be. You just need more people to do things now because of this pressure to get things out faster and not being able to explore. And I will take this in comparison to what even Sutherland did with Sketchpad and early work here, is that for all its faults, the reason that academics has the ability to greatly influence things and come up with these great ideas is that by design, they are not pressured to get something out as fast as possible. And not only that, but they are by nature exploratory. Even Sutherland had to come up with those ideas behind Sketchpad, you know? And not only that, because it was his PhD thesis, he had to kind of create a set of ideas and constrain them in a way to be unique, but also solvable by one person. You cannot get a PhD by hiring a bunch of people to do your work for you. That's very much frowned upon. So it's one of those things where that allows for a lot of interesting innovation to occur. And increasingly, that's not able to happen for a lot of people because A, they're not in the academic environment, but B, there's just this constant pressure to get things out as fast as possible. And not only that, but I would say developers themselves have kind of surrendered themselves to this idea that the only way they can be judged as a good programmer is being able to put out a certain amount of code in a certain amount of time. And the faster they can do both is the only measure of their value. And That's really, really hard. Not only does it lead to just poor software in general, I would say that the quality of software that we've seen is more available than ever. It's used more than ever, but overall, its overall quality is lacking in a lot of regards. And certainly, we're just seeing a lot of cases where it just seems to be worse and worse. It's one of those things where it's like, how many times do we go to? It's like, oh, there's yet another change in a mobile application that makes it even more complicated to do something. That's great. So we've kind of uh, not allowed developers to make better software, have higher quality, but we've just basically put them on a treadmill that'll eventually just burn everybody out. The second side of this that I want to talk about is the functional programming. And just a plug, I do a lot of videos in the Racket programming language. So if you want to learn more about functional programming in the context of Racket, which is an evolution of Scheme, I would suggest those videos. Okay, plug over. The interesting thing now is I see a lot of people in the programming community that discuss functional programming as being opposed to OOP and, in a sense, replacing it. So they're taking this old school thing where it's this old school class hierarchies plus message, old school data types plus function, new old school. There's acknowledgement that these are old ideas, but basically that we're kind of overcoming this clunky OOP idea, and we're going to use this new great thing called functional programming to solve all this stuff. And the interesting thing when I see in a lot of the discussion is they ignore the fact that basically functional programming itself brought in object-oriented programming concepts before C++ even existed. The perfect example of this is the Common Lisp object system, which was influenced by earlier work on two systems at MIT called Flavors and Common Loops that did things like introduce the notion of dynamic dispatch and message passing. For those of you who are familiar with Smalltalk, that sounds familiar. It should, because that work was really influential on what Alan Kay did with the Smalltalk environment. And this whole thing is its own interesting branch of object-oriented development that maybe did not influence C++ as much as the work that was done on Simula and Algol 68. Where it did have a lot of influence was in Objective-C. And the reason I bring that up is that Objective-C was also a very successful foundation for a GUI programming environment called NextStep. And this whole kind of computing that came up, some people that may have used Next boxes, remember those back in the day, Next workstations, but most people will know NextStep as being the foundations for what ultimately ended up with OS 10 on the Macintosh and that new programming environment. And Objective-C for a long time was the default language for doing those types of things. Now, the reason Objective-C was replaced is that it doesn't quite do the right thing, and Swift was designed by Apple to actually quite do the right things and overcome some of the limitations that C presents. Basically, Objective-C is you still have the problem of memory management, and while you don't really necessarily want to have full-blown garbage collection, even though that works really well, you need to have some kind of way of tracking what's going on there, and you need to have something like the ARC and in Swift and so on and so forth. So Swift really kind of solved that problem better. But this whole idea from Common Lisp and Swift all the way to Swift is its own interesting way of doing object-oriented programming that still also used the notion of classes and still in the backwards way could kind of do inheritance through metaclasses and other types of things. So, but again, I want to emphasize that this work was starting before C++ was even an idea. The second branch of where this has happened is something called OCaml. And OCaml brought in object-oriented ideas into what was called the ML family of languages. And the reason being is it kind of started out with this language called Standard ML, developed at Bell Labs, excuse me, it was ATT Labs at the time. And it's interesting in the fact that it's the progenitor of two languages that I really like, and one that's actually quite popular in terms of people really like to talk about it. Everybody seems to want to be able to use it all the time and wish they were really good at it. That's Haskell. And then there's F#, which is also kind of its own variation, very much inspired by Haskell, but also very interoperable with .NET. And it's really interesting to look at objects in OCaml and how they interacted with previous concepts that people are really touting as the right way to do things like data types and all this types of stuff, and records and discriminated unions, and how they actually integrated with those types of concepts and make it in a very deliberate way, and not just to be trendy, but in a recognition that basically, yes, class hierarchies can bring in a set of semantics that can be very useful for solving certain problems. Where I think this is the most interesting intersection and maybe the most successful commercially is C sharp. And C sharp adopted a large section of functional programming in this kind of Java like OOP environment by introducing things like lambda functions, link, which is basically bringing things like map, filter, select many, which is basically flat map, and all these basic fundamental functional programming operators into this object oriented environment. Um, and that was enabled by how they approach generic types. In C sharp, generic types are part of the type system. They are not erased as they are in Java. So when C sharp adopted generic types, they made a deliberate decision to basically obsolete the older classes that were not generic and replace them with generic versions and go through this range of being able to port that code over. They had the advantage that they had the ability to do this because it was a much younger language at the time. Java did do generics, but they decided through type erasure because of the backwards compatibility problem, and they wanted to be able to not have to do a new version of the JDK. They're very focused on that. But Java also later brought in these ideas with streams, so they have their own version of map and stuff like that. That being said, because of generic type erasure, that model is pretty complicated and has a lot of, I would say, warts. Or it just it's not as consistent as C sharp is, and the reason being is that, as an aside, quickly to say the reason being is that C sharp can now actually, because of generic types, can express the type of a lambda function or a link operation via anonymous types. And not only that, but basically it can have basically you can have an interface like action T, which action T TT1, which represents a lambda that doesn't return a value, and then you have something like T function T result, which is basically this is a function that has a one argument variable type T and returns a value of T result. That allows you to type a lot of these operations that Link is doing, being able to do and then do various things like type inference, type checking upon them. If you erase them, you have to do all sorts of weird stuff when you are talking about how you orient the string model, where it just doesn't become, oh, object translates to other object. Now, of course, there are specific languages that tried to bring in much more robust versions of functional programming into the JVM environment, Clojure, Scala, and to a lesser extent, but some still interesting ideas in Kotlin as well. The last thing I want to talk about is kind of an interesting aside here is that when I talk about basically people looking at functional programming as basically replacing this object-oriented paradigm, a lot of what's being done here is work in TypeScript and by definition JavaScript. And just a little history, TypeScript was kind of developed by a lot of the people that did C Sharp to kind of overcome some fundamental limitations with JavaScript. And mainly this is around the developer experience and the fact that you didn't get like auto completion. How do you use libraries? And all this kind of stuff to make it a little bit easier to program in. Basically, so that if you had an object and you went dot and hit, control space, it couldn't tell you what was going to come after it. And if you put if you put in something, it would just return, oh, I don't know what that is. And it couldn't say, oh, you typed that thing wrong. That's not the function name. That doesn't exist. So trying to add some of that information to it. And they did a very interesting job of it. And it initially actually they added a lot of concepts and it did help a lot of people. And there's a lot of very, very popular web frameworks that kind of demand the use of JavaScript, even though some people kind of do not like the additional type complexity, that they kind of want to just be able to have the freedom of JavaScript and just kind of use that duck typing system as it is. But I would just kind of say here that basically, if you look at the web ecosystem, TypeScript is embedded enough into it that it becomes an interesting thing to talk about in terms of being in opposition to traditional object-oriented programming languages. So the thing about it is that it's successful, but TypeScript, in my mind, hides the limitations of JavaScript at a pretty large cost. The first thing about it is that JavaScript itself uses prototype-based OOP, and functions for arbitrary return values in this case, often ends up being overly flexible. And where this comes up is that in order to handle this flexibility, the TypeScript type system itself has evolved to what could be called a dependent type system. Not a certified dependent type, but dependent type system. And I won't go into the theory of that because it's actually very complex. But basically what it is that the type system itself, a dependent type system, can be vastly more complicated than what we are used to in terms of types. And what that has led to is that the idea of TypeScript and being able to create a better development environment and in terms of autocomplete and understanding and program analysis has been now increasingly defeated because the process of creating that information from TypeScript code can be so slow that the experience is just miserable. There are code bases in which you will try to do an autocomplete on a certain TypeScript thing, and the language server process will literally take 2 to 3 seconds. Now, recently, apparently, there's been some work to really speed this up. But the fact is, it is not instantaneous in a lot of cases. Not only that, but the complexity means that in certain cases, the language server process itself has to be restarted a lot. Things can get really gunky. So much so that the type checker that does this is being ported from TypeScript. It no longer bootstraps. It will be ported to Go. And it's not a rewrite. It's basically a code translation for the TypeScript code to Go. The team realized that it was actually too complicated to try to rewrite, and that they had to solve these problems now. They couldn't wait 3 years to get a new version of TypeScript out. And so they're having to do extensive amounts of caching, all this crazy stuff to get the type checker to work, compared to these other languages in which type checking should be just instantaneous. You should never see any lag from, like, if I want to do autocomplete on certain types of environments. If I was doing C# programming in Visual Studio or Visual Studio Code, and I did an autocomplete and it started lagging on me, I would wonder what was wrong with my computer and if something was going on. I would not expect it to be just a price of, well, the ecosystem not quite being there yet. And I am not envious of web developers in any stretch of the imagination. I feel so sorry for all the things that they have to do just to get some of this stuff to work. And like I said, the reason I kind of am so skeptical about some of this stuff is that when I look at my experience with debugging C# in Visual Studio in 2015 and 2019, it is miles better than what the debugging experience is now in 2025. And if you take a look at C and C++, going back even 20 years, in some sense, debugging that was even easier than what people have to do to debug some of these code bases in TypeScript. It's just really crazy. To finish off, all languages have issues. Of course, TypeScript suffers from JavaScript being rushed, not designed. This is something that I think is really interesting, is if you take a look at the history of these languages, they were built on some very solid foundations and a lot of research. JavaScript didn't have that luxury. It happened to be something that somebody thought was a cool idea, got rushed into production, and stuck, because sometimes worse is better. The thing I want to also point out to is that it is not that the idea was that, oh, prototypical object-oriented languages haven't been fully explored, and we don't really understand how to use them, and to do all these other types of things. That is not the case. There's a language and project called Self that was being developed in the 80s. It started as basically an offshoot from Smalltalk. And it came up with this idea, instead of having meta classes and other types of things, class hierarchies, it went with this idea of, oh, to make an object, you don't have to have a class, you have a prototype, and that prototype expresses that structure, and you copy the prototype and mutate the prototype in different ways. The thing about that is that work was being done, there's some interesting things about it, but it was already being eclipsed, and very obviously being eclipsed, by other object-oriented programming languages and concepts before JavaScript even came out. So the thing about it is that the jury was kind of out on prototypical object-oriented programming languages in terms of the research community, but for the reasons of being expedient and quick, it was put into JavaScript, and those limitations have stuck ever since. So the thing about it is that when people argue about, oh, people just don't understand how object-oriented programming is. No, they have done a lot of research on it, and it was rejected by the mainstream. And there's some very good reasons for it. And the reason being is that, again, in general, it's too flexible for the ideas of object-oriented programming in terms of being able to protect programs from certain types of evolution so that they do not become cancerous or metastasize and grow out of control, but that they evolve carefully and last for a long time. So I'm going to argue that this was not a fundamental wrong road taken here. Not only that, but some of these side roads that some people say is like, oh, why didn't we do this in terms of fat struct, so on and so forth, were explored and were actually put out there and fought in this environment. But for various reasons, the class-based inheritance model stuck. And not only that, but functional programming has been added onto it in the case of C# and other languages. And some other languages, but especially C#, has been added and integrated into a very powerful combination. And so there's very much more synergies here that are available versus being things that being opposed to each other. Of course, there's always going to be new ideas on the horizon, and so on and so forth. But the thing about it is that I would say overall, this programming model was not necessarily something that just was this big, huge mistake, but it's actually something that overall was a big win. And despite some people not liking it, and here's what I'm going to point out, and I will make this statement to everybody: it is not hard for very talented programmers to make programs in more flexible and powerful programming paradigms. The problem is that not all of us, including myself, have the luxury of being that good. And so certain concepts which restrict those types of that flexibility do add to the overall quality of things. Constraints are good. It's not only in a lot of things, it allows things to happen at all. If you could just have every possibility, it's very hard for you to do certain types of things. You get just overwhelmed with all the choices. So when people say, oh, I don't want to use C++ and I don't need it, I agree with them. There's a lot of people that can do excellent work with conventions, just use C, use other languages, and they do a very, very good job at it. The thing about language evolution is it is trying to make the average developer more productive. And I would argue that C++, Java, and C# combined with the ideas from COM, ActiveX, and Visual Basic overall did make developers more productive. And that is ultimately what led to the demands for web-based software. And as we move through that, hopefully that ecosystem can be more supportive of developers so that they can also take advantages of better programming tools, better environments, and make that next leapfrog into, make that next leap into another level of productivity. Anyway, if you like this and made it so far, I will be doing some other presentations down the road on this channel. I will be talking a little bit more about Rust. I'm kind of interested about how that type system evolved and how they use the concept of structs and traits versus class-based inheritance. I will do a little bit of talk about dependent types for verification and proof checking, because I think it's a very interesting type of thing. And it's an interesting challenge to make that understandable to people with maybe not just a graduate level of understanding computer science. And finally, it's one of those things where with all this talk about object-oriented this, functional programming of that, the question is we really just need to start programming in Haskell, or maybe not even just Haskell, but Bracket. So that should be a really interesting talk. Again, thanks for watching. If you like this video, please leave a comment, like and subscribe. Feed the YouTube algorithm with all the things that it wants to make sure that my channel exists. I really do appreciate it. Thanks, and have a good day.